Okay, stochastic local search. What I want to talk to you today is what do you do if you, Eduardo had a very nice talk to show how much effort you can put in to solve something to global optimality, to proven global optimality. And of course, from a mathematical point of view, that is what you want to do. But then sometimes you're in a situation like Kai, where there is all kind of a bit shitty data, and you just need some good enough solution, whatever good enough exactly is. And that is actually where heuristics come into play. That is usually a way where you try with not so much effort, get good solutions out of the problem without too much proof of how good it is. And I have to say, problems are different. There are some problems which are kind of primal difficult and some who are dual difficult. So primal difficult means it's really hard to find the optimal or a good solution, while dual difficult means it might not be so difficult to find a good solution, but proving its optimality is another matter. And this depends a bit on the type of problems and your formulations. Sometimes it's more than the other. Okay, so does this work? No. Here. So just repeat this here. You had this before. This is basically a definition of a combinatorial optimization problem, which just says we're minimizing some function depending on x, and x comes out of some set, which is in some way defined by integers, and it's limited. It doesn't matter. We don't need it anymore. I just wanted to put this up that we have a vague idea of the stuff we have here. Yeah, but it's roughly the argument. And an important point is that you can reformulate stuff. So if you have such a problem, you can also put this as a decision problem. If you just say, well, do we have a solution with 26? So you just put the objective function here there into the set and say, oh, we are just taking solutions where 26 is the answer. And then you have all put the same to the question, is actually X empty or not? That's a way to make it a decision problem. You can also do the other way around and can put the constraints into the objective function in the way like here, where you put the f of x and the objective function here and the constraints into it, and basically give a penalty for violating the constraints. So in that case, it's always feasible, but it might be, well, the optimization problem is feasible, not your original one, but you have this penalty there, and then you minimize, and if the penalty goes away at some point, you will find a feasible solution. It makes much better to get a start with. So in that case, it's kind of trivial to find some x out of x. It's just a question how you formulate stuff. So in the end, to solve a problem to optimality, you have to do two things, and that is kind of important to remember. You have to find the minimum x, so there exists one. And the other is to have to prove that there exists no better x. And that is actually what a lot of people think that is the reason why P is unequal NP, and what is the difficult thing on NP hard problems, the proof that no better x exists, because you have this for all. I mean, for all is usually more difficult than there exists one. I mean, you can see this on a court case to prove, oh, somebody has seen you to kill this guy. It's very easy, there exists one to prove, but saying we can prove nobody in the world has seen you doing that is much more difficult. That's kind of the setting. And what we, do you need Lautstärke erhöhen? Okay. And what is important here is if people talk about solving a problem, the question is, what do they actually mean by solving? So if you ask a theoretical computer scientist, yeah, he typically, if say the problem is solved efficiently or something, he means proven optimal solution to every possible instance of this problem with at most this effort. So it's kind of a bit of a worst case approach usually. If you ask an applied discrete mathematician, so me or somebody, I would say, well, practical compute within numerical tolerance is proven optimal solution to these particular relevant instances of the problem class in reasonable time, which is not exactly the same. And then there are a lot of people who just say, oh, find a good solution to this selected particular instances of the problem. I mean, I am currently, this slide actually is from another talk. I'm having a lot of discussions with the quantum computing people lately, and they usually just compute some solutions. And actually finding some solution to a traveling salesman problem is not difficult. Actually, even finding a solution within 10% or 5% of the optimum is usually not difficult. Yeah, but proving optimality is, and they just ignore this. And there's really a lot of papers which start as here is an NP-hard problem. I mean, NP-hard translates for the theoretical computer scientists as intractable. And then they say, oh, here's this problem. It's intractable overall, but we can find a solution for it. And this was never difficult. Yeah, so be a bit careful if you read this stuff. Okay, so yeah, we talk today about, or I will talk a little bit about stochastic local search. Stochastic means we do something random. Local means we do it near to us. Search is we look around. And heuristics means we do not expect to be perfect outcome. Yeah, and I just give you an example how to, I mean, imagine this. So what does local actually mean? So if you go, let's say, traditional evolutionary algorithm, so outside the world, and I ask, I want a fierce mammal. Yeah, I want a fierce mammal, and I go to Australia. Yeah, then I wait 100 million years. What do I get? What is the most fierce mammal in Australia? Any idea? Kangaroo isn't, yeah. What? Actually, the wombat. Yeah, it weighs up to, it's 1.20 meters, up to 40 kilo, has sharp teeth, really sharp claws. And if a predator comes, it pushes, it has a kind of a reinforced back. It pushes, the predator goes into a tunnel and pushes the predator with its back against the tunnel to suffocate it. Yeah, so this animal here. Yeah, this is what you get as a fierce animal after, well, 10 million or whatever years. Yeah, and then, but it's locally the winner. And then you go around, look around, you go to New Zealand. And then your wombat is still king. I mean, there's nothing in New Zealand which can threaten a wombat. Yeah. And then you go on, go a bit further. Let's say you go to India, and then you find something that's more like a global optimum. And, yeah. And you see that you had no clue how good your solution was in comparison to everything. Yeah. And it's always a question, what is your neighborhood? Because of course, if you go further, you might find something that even rips a tiger apart. Yeah, so it's really a question there. And local means you are just in your neighborhood. It might be very good, but you are not sure how good it is on the total scale of things. Okay, so then we have a lot of heuristics and things who are kind of physics or bio-inspired. And honestly, well, there's this thing. Have you ever wondered why in natural medicine there are so many things made out of tigers or something like that? Yeah, if you have tiger teeth and tiger this and that, and they are all basically, if they get a tiger somewhere, they dissect it totally and make it in a lot of funny medicine for people who believe that eating something of a tiger makes you as strong or as whatever there is. Yeah, this has been done by people for millennia. Every animal that is particularly dangerous or poisonous or strong has been put into something of medicine, and people eat it and think it confers some of their properties to them. Yeah, and that's basically the same thing that that happens. Evolutionary algorithm, genetic algorithms, simulate annealing, and ant colony optimization, intelligent water drops algorithms, slime mold algorithm for stochastic optimization, naked mole rats, whatever this, how this works. And basically, the idea is the same. Inspired means it helps to find a catchy name and leads to some positive, but usually wrong associations about the algorithm. Yeah, so just forget about the name, look into the math, and the math is usually that stochastic local search. Yeah, which means you look randomly around in your neighborhood and try to find something. Yeah, that's it's all kind of the same. I'm not saying that it's bad. I will come to that, but you have to have the right thing. I mean, forget about this ant colony, whatever bullshit they are telling there. This has nothing to do with ants or with colonies. It's just a heuristic in some way to do some things, and I will show you how they kind of work. In general, if you want to optimize something discrete, there are two basic optimization algorithms. This is now super high-level view of it. There is what I call the space explorer. Yeah, you enumerate the feasible points in a solution space, either explicitly or implicitly, typically by some kind of search tree or whatever. And of course, it's super important that you implicitly exclude as much of the space as possible. But basically, it's enumeration. And the other is, yeah, and it's, for example, nice if you have the convex hull of the feasible points known or something. That is really nice then. The other is a pathfinder, more continuous. Select some starting point. From the starting point, you have some stopping criteria. And as long as it's not fulfilled, you look for a direction. You look for a step length. And then you made a step. Well, and yeah, this is the other type of algorithm. There are lots of them, all kind of gradient descent or whatever. You're just here, you look for some direction, you make a step, and you hope you are nearer or not than before, and you continue this until you are. So there is, of course, important finding good starting point, how to compute a good direction and have a step length. So if you have a convex gradient and a gradient available, of course, it works much better. Yeah, but this is the basic mindsets for optimization. And a big question is, of course, what do we know about our feasible regions? Yeah, can we evaluate the objective function fast? And will we get a local or global optimum in the end? And for example, for heuristic idea, we can just hop around randomly in our feasible region and hope that we get something good. That's not, if we do this enough hops per second, I mean, you find a lot. If you have a good heuristic, it might make 1 million tests per second, then you will find something, usually. Regarding feasible regions, I mean, this is a convex feasible region, which is really nice because you know it's inside everything. But of course, it can be non-convex. Then you have this problem that there might be something in between 2 points. It might actually be non-continuous, yeah? That it's difficult. If you have a non-linear objective and a feasible region, which is non-continuous, hard to do. It can be discrete, then it's just the points there where you are. And of course, it can all of this at the same time. So you have some points here, there, and then it might be really difficult to find something. In a certain sense, I would always claim that for all these difficult, I mean, NP-hard optimization problems we have, especially nonlinear, if they are really super nonlinear and everything is as difficult as it can be, well, we will not be able to solve them. I mean, the worst case, they're undecidable. They're usually if we are in a box, but still, it might be just 1 point in a huge space where we know nothing about. So can happen. But usually we are optimists and think our problem is not as difficult as we thought. And therefore, then we kind of try to be lucky. Okay. Just one more thing to think about. If you have a binary integer program, so you have 0, 1 variables, then what you do is you look for corners at the hypercube. Yeah, you have a hypercube there, an n-dimensional hypercube, and all you do is look for corners. And if you have a cutting plane, it cuts off some corners. That's what's happening. And if you have some kind of local search or whatever, I mean, you jump basically from one corner to the next, and you hope that you jump around. The only problem is that we have a little bit problems imagining 1,000-dimensional hypercubes. At least I have sometimes. Yeah, so that's the thing. But actually, it's just always a corner. If they say some landscape, it's just corners. You just jump from one corner to the other. Okay, then there is these, there's no free lunch theorem, which I should at least tell you. And this says that basically all algorithms are as bad as the others. You can just basically say, okay, I get better on this particular instances, but then you will get worse on others. That's probably in a sense true. And what we always do is that we trade generality for speed. So we get more specific, and then for that we get faster. I mean, you had in the Eduardo's talk here, he said we have a very general model. We compare ourselves to the best specialized algorithms, and sometimes the specialized algorithms are faster because they have an easier task. They are just specialized on exactly that. Yeah, and so you can pay. But what you should not forget, while this is a general argument, we are not interested in all instances the same. There are relevant instances. I mean, you can construct a lot of funny instances for variable routing problems for everything, but we are usually interested in practical, particular instances, like whatever delivery hero wants to deliver. This has certain properties. So that is one thing to take in mind. And then having an algorithm that is good for that, what you're actually interested, is not that bad. Okay, so stochastic local search. So we start with some arbitrary solution. That's always the way. Then we repeat until our time runs out, usually. Randomly change something. If the result is better than before, we remember as the current solution. If we have no improvement for some time, we allow some changes leading to a worse but very different solution. And we continue this as the time runs out. That's actually this scheme. Of course, steps 3 and 5, so this random change something is super important. And step 5, how you allow a change that is worse but different is important. With a change, this is something that I will later come to something like simulated annealing, where you just flip a variable, for example. If I can say I flip integer, a binary variable. Of course, this is the smallest change you can have. But if you know something about your problem, then of course you make more interesting changes. For example, if you have vehicle routing problem and you have some imagine you have some route here, whatever goes there, then you don't flip one variable, you always flip two. I mean, you remove two things and then connect them the other way. So a single switch is just one change in your problem. So there are lots, you can make them arbitrarily complex. I mean, if you understand your problem, it's just coming from one point to another, and depending on your problem, you might do a lot there. Okay, so the whole thing works usually best if feasibility is easy to achieve. And it's important that its iteration is fast. If I implement simulated annealing and you do this for qubits or so, if I do this fast, I really do, I don't know, nearly a billion iterations per second or something like that. And then you can try a lot and you find something, no question. It's usually easy to implement. Okay, so this is a pretty good idea if you have not so much mathematical understanding or knowledge about your problem, or you don't want to invest so much time and work into this, but you just want a relatively good solution fast. That can be a very good way to do. Okay, so one more thing. If you just imagine, I have something on this slide. Yeah, I mean, assume you have a constraint optimization problem like that. We had this before with 0, 1 variables and one opt. You just run through it and flip every variable and see whether it gets better. If it gets better, you do this. If not, you reverse, you go back. And then you run through and then you repeat this until nothing happens anymore. Then you are kind of one opt, yeah, because no single change will make anything better anymore. Next is, big surprise, 2 opt, where you do this with pairs. Yeah, you flip 2 pairs and see whether anything gets better. And do this until you find nothing. 2 opt is super important. If you ever work in practice, your problem should be 2 opt, because this is the most you typically can see. If you have a solution that is not too optimal, even though you can prove you are 0.1% near to the optimum or whatever, you show your solution, some practitioner looks at it and says, but if we flip these 2 things, it gets better. And then your reputation is done. Even if you say, oh yeah, but it doesn't make much of a difference, but it gets better. Why didn't your algorithm find this? Yeah. So whatever you present, make sure it's 2 opt. That is really, really important. And of course, you can also do this with more flips. I mean, you can do 3 opt or whatever, but it is then to the power of 3. So what you typically do is you kind of chain this. So you make some flips, and as long as you are on the improving side, you continue making more flips. And there are some elaborate schemes, especially for TSP problems. There's Chain-Lin-Kernighan heuristic, which was a major step forward. And if you look at the latest heuristics for TSP, they give you very, very good solutions. Actually, TSP is one of those problems which is not primal difficult. It's not difficult to find a very good solution. It's very difficult to prove its optimality later on. Okay, yeah, this is what I said. So here is, what is this? Yeah. Here is one of the very famous heuristics, simulated annealing. Forget about all the annealing thing. What it's basically doing is you do so and so many iterations. You start with some arbitrary starting solution, whatever that is, doesn't matter. And what you do then, you have this temperature thing. And this temperature thing basically has an influence on the probability that you change something. So you pick a random variable, whatever, so a small change, and then you check whether this change improves the whole thing. If it improves the thing, you do it. If it does not improve the thing, this is actually step 6 here. So this would be, can you see this? Here. Here. This is a case that actually gets better. If it gets better, you take the new solution. If it does not get better, then you have here some funny term that is a probability that you take the change anyway. So even if it's getting worse, you take it. This allows you to get out of local optima. And the lower the temperature, the less likely it is that you do this. So at the beginning, you have a high temperature. So you might jump, even though it gets you quite some worse. If it gets then cools down, it's less and less possible thing until the whole thing basically becomes a one-opt at the very end. Of course, as I said, this is now, if I talk about single flips, but you can have more complex changes for this. Yeah, that is simulate annealing, and this works surprisingly well. It's easy to implement. If you do this right and your problem allows for quick changes, then, I mean, that you can several million checks per second, it works quite well. Again, it's important to have the right changes. If you think about the TSP, if you have an edge, a variable for every edge that is in your solution, if you change an edge from being there to in the solution to not, it gets infeasible because your tour gets disconnected, right? If I just have a tour, I remove one edge, it gets disconnected. So what you always need is basically 2 flips. You need at least to make one away, or actually need 2 away and then reconnect them. That is the smallest useful flip you can do in a TSP. And if you can, of course, achieve this by single flips, but you need several of them, which means if you just put a TSP into this scheme with single flips, the probabilities get much worse and it will not work as well. Yeah, especially if it gets bigger. So having the right kind of flips here is super important. The other big thing, the other very famous one is Tabu Search, which is a bit different. So same thing, you start with some solution. You have this T as a taboo list. And what you then do is, again, you repeat until you are finished in some way. You look through all or some subset of neighbors and look actually for the best one. Yeah, you take the best of your neighbors to change. And then you change this. If it gets better, I mean, you take the best. So you should find one that is improving, or you take the one that is least non-improving, and you add it to your new solution, to put it in the new solution. But now is something important. You put it also in a taboo list and say, for the next 50 steps, I will not allow to touch this variable again. This is to protect the thing from switching forth and back, because if you have a solution that gets just a little bit worse, you make it a bit worse, then you check for the best next round for the best you can do, and this is doing it back, and then you're just flipping. So you have a taboo for whatever 50 or so and so many steps. You repeat, and then you do this, and that's Tabu Search. Also works quite nicely in a way. But there, as I said, in the end, it's a general scheme. You start with some solution, can be random or whatever. You pick something to change. You change always if it gets better in a sense, and then you just have to make sure you don't cycle and you get out of local optima, which is that you are locally, you have sometimes to get a bit worse to see some different solution. Okay, evolutionary algorithm. Similar idea. You have a general initial population of individuals, can randomly generate them, so you have some stuff. You evaluate some fitness function on it, objective function, call it, and then you select the best of them and kind of combine them. Like you take the first half of the one solution, the second half of the second solution, and combine them. Again, it depends, of course, on your problem. In the ideal case, you want to do something problem specific, because if you take the first half of a TSP and the second half of a TSP, it's probably not working that well. But that is, then you get this new thing. Then you do some mutation, which is random flips, just to make sure you get out of your local comfort zone. And then you put this in the pool and you repeat the whole thing. I have put this, I hope this works now, that you can imagine how this algorithm actually works. There were some good things. So here. Yeah, this is your initial pool basically here. Yeah. And what is really important is what you see here is that your pool is diverse. Yeah. That is for these kind of algorithms totally important that you have a diverse pool and then you start mixing the stuff. Actually, I wanted then to show some patch up monster and I tried DAL-E to generate a picture, but it refused. It says it was against its policy or something. Okay, and then the next is from then you come and then you make kind of selection of the fittest. Yeah, you evaluate the things and see how this works. And this looks basically like this. Yeah, you go through them and then you see what you can find there. And whatever is a survivor, this then continues. There, of course, there are different ways to do this. I mean, this works as well. You just need to find some way to evaluate your stuff and decide who is going to continue and who is out there. Yeah. So yeah, this was when I tried to get this thing there. How much time do I have? Yeah, well, I should speed up. Okay. Here's one interesting thing is we looked in a MIP solver how long it took until you get the first solution and when you find the last solution. And the thing is what you can see here is basically we find a solution immediately, nearly. And for most problems, you find the last, that is the best solution before you have the lower bound there, because this is typically how it works. And the thing is, this means if you want to speed up your MIP solver or your exact solver, heuristics usually don't help you much because you will find the optimal solution very often before anyway. There are something like reduced cost fixing, so it helps. But there's a very nice paper by Timo Berthold about the primal integral, which basically gives you the space here in between, which shows you that if you have a better solution fast, it's actually an advantage for you, especially practically. Okay, I skip over this a bit. This is about quadratic unconstrained optimization. That's not so important here, other than for max cut. But what I want to show is this. We have actually currently the best QBO solver, even if you get the latest numbers. So this QBO, and this is numbers in seconds we need to optimize to proven optimality these problems. Yeah, you see there the instances, they are here. And that is the number of seconds we need to optimize it. But then there is a Japanese colleague of mine who has a GPU-based stochastic local search heuristic, ABS2. And this is the time in seconds ABS2 needs to find the optimal solution for these. So basically for all the problems, apart from 2, it finds the optimal solution and usually in 0.0 whatever seconds. Yeah, so these problems are dual difficult, not primal. It's relatively easy to find the solution, but to prove its optimality, that is difficult here. And that is what I want to say. So if you just want a good solution, this heuristic is certainly a better way to do. I mean, I'm not saying how long we need to find the solution, but it's just you can find them very, very fast. Thank you.